Featured video is my idea of a solid-state heat engine, and I believe it can have a high power output. I'll show you why I think that in a second. First, let's look at the basics of the design. The engine is designed of 4 main sections. Number 1. Wires or even rods. Here I intend to use memory-shaped alloy wires. I believe that any material could be used here, but I'm not sure yet. Certainly the featured engine is designed to be used with memory-shaped alloy wires, and it would at least have to be modified for use with some other material. The second section is the basic disc. It provides the base, hence the name, and rotates with the shaft. The basic disc will have wires attached at one end. The third section of the engine is the spiral guide. It is basically a pipe cut in a way that it redirects the pulling force of the wires into rotation. This section is static and does not rotate with the shaft. The last section of the engine is the active disc. This is an assembly made of springs and other parts that move with the pulling of the wires and press against the spiral guide. More on that later. Of course, there's also the support structure like the shaft and the bearings and other parts and assemblies which enable the motion and stability of the engine. Let's look at the details of the heat flow and energy transformation from the heat flow into mechanical energy. By mechanical energy I mean potential like the tension of the wires, or kinetic, which is the rotation of the shaft and all parts attached to it. The heat flows from hot to cold reservoir. This case is about hot on the bottom, which could be hot water, and cold on top, which could be ambient air for the memory-shaped alloy I intend to use. It could also be reversed and sun could power the top and earth could cool down the bottom reservoir. Every heat engine works by transferring the heat flow with the medium that it has its core. The arrow here is showing the only place where this heat engine is transforming the heat flow into mechanical energy. In this engine, the core are memory-shaped alloy wires, and the amount of heat they transfer from hot to cold is at most the amount of mechanical work they can produce. And that amount is proportional to the mass of the medium in the heat flow. So the more material there is at the core, the more heat will flow through the engine and the more work it can produce. Per unit time, that's power. And there lies my belief that this could be a high power heat engine, because it transfers much more heat with the wires, that's the key point, than other engines published as solid state. For example, take a look at this engine where the circle marks the amount of material there is in the heat flow. It's little. Imagine you could have hundreds of times of that amount in the same heat transfer region. And that is what the featured engine provides. A lot of material in the heat transfer zone. Now let's see how the spiral guide redirects the pulling force of the wires dipped in hot water coming from the cold air. First, we need to assume that the wires contract by roughly 4 to 5% of their initial cold length. For example, if a wire is 300 millimeters long, then by dipping in the hot water, it will contract by 12 millimeters. That's the beauty of the memory-shaped wires, especially one in particular that is Nitinol by Nitinol. Once we have the pulling force from the wires acting on the spiral guide redirects this force into rotation like this. The radial component turns the wheel with the wires attached to it, and by turning of the wheel, the next cold wire comes in contact with the hot water. There is one more important detail of this engine's design, that is the active wheel and the crucial two elements in its design, the spring and the bridge with the pulley. The way the spring is currently designed, I'm not sure how much the spring can move until it will touch the spiral guide. The reason is just the way the spring moves when pulled by the wires, like this. This detail needs improvement. All I know is that I want to proceed in the spirit of the compliant mechanisms. Finally, let's assemble the engine from the ground up. The pillars and bearing housing, the bearings, the shaft, spiral guide, basic disc, active disc, wire clamps, and finally wires. 185 meters on 36 segments for this engine. One segment is 300 millimeters long and has 17 wires in parallel. This is the active disc with the springs and the bridge. There are 36 units, 10 degrees spaced apart. The bridge is laser cut and holes are drilled later. They are M2.5 and M3. I would like to thank all my viewers and supporters for being a part of this. Thank you.